Today I'll solve one fluid mechanics numerical problem based on dimensional analysis. I'll use Rayleigh's method. So here is the problem statement. Using dimensional analysis, find the expression of power developed by a pump when power P depends upon the head, discharge Q and specific weight W of the fluid. So first dimension of each variable. To find the relationship between the variable, we first write down their dimension based on the fundamental physical concept. So first is power. Power is defined as the rate at which work is done or energy is transferred. Mathematically, power is expressed as work per unit time. So work is defined as force, time, distance. Force has dimension F, that is mLt to the power minus 2. So mass, time, acceleration. Therefore, work has dimension W, that mL to the power minus 2 multiplied L. So mL to the power 2 to the power minus 2. Since power is a work per time, so the dimension of P, that will mL to the power 2 t to the power minus 2 by t. So that is mL to the power 2 t to the power minus 3. Next is head, H. Head represents a length or height in a fluid system. So thus its dimension is simply length, that is dimension is L. Next is discharge. Discharge is the volume of the fluid flowing per unit time. So volume has dimension V, that is LQ, and time has dimension T. So therefore discharge has the dimension Q. LQT means LQ to the power minus 1. Next is specific weight. Specific weight is the weight per unit volume. So weight is the force due to gravity, so it has the same dimension as force. So that is mL to the power minus 2. So mass, time, acceleration. And volume has dimension V, that is L cube. Therefore specific weight has dimension W, mL to the power minus 2 by L cube. So that will mL to the power minus 2 to the power minus 2. So after getting all this dimension, so we will apply Rayleigh's principle. So fundamental dimensional equation. So let P power be proportional to H to the power A, Q to the power B, W to the power C. So the equation can be expressed as P is equal to K, H to the power A, Q to the power B, W to the power C. So where K is the dimensionless constant and A, B, C are the exponent to be determined. So now how do you determine that? For that we have to substitute the dimension of each variable into the equation. Okay, so here the dimension of P, that is mL to the power 2 to the power minus 3, and is equal to H is L to the power A and Q L cube to the power minus to the power B and W to the power C. So W's dimension is mL to the power minus 2 to the power minus 2 a whole to the power C. So now simplify. So mL to the power 2 to the power minus 3, so is equal to L to the power A, L to the power 3B, t to the power minus B, m to the power C, L to the power minus 2C, t to the power minus 2C. Now equate the power of m, L and t both side of the equation. So first so from here, so m power is 1, this side left hand side. Now that side right hand side, m power is C. So 1 is equal to C, so C will be 1. For length, so left hand side 2 and A plus 3B minus 2C. So here, so 2 is equal to A plus 3B minus 2C. So 2 is equal to A plus 3B minus 2 into 1. And then for time, t to the power minus 3. So minus 3 is equal to minus B plus minus 2C. So minus 3 is equal to minus B minus 2C. So C is equal to 1. So from here we can plug that, and from this equation we can easily find out what will be the A, B, C value. So C is equal to 1, and from length equation 2 is equal to A plus 3B minus 2. So A plus 3B is equal to 4. From this equation minus 3 is equal to minus B minus 2 into 1. So that B is equal to 1, and if I plug here, so A will be 1. So we got A is equal to 1, B is equal to 1 and C is equal to 1. So the dimensional equation is P is equal to K H to the power 1, Q to the power 1 and W to the power 1. So P will be K H Q W. So that is the relation C between P and other variable H Q W. That's it. Thank you.